Welcome to our latest video on making ammonia, the Haber process. This video is suitable for GCSE students. By the end of this video lesson, you should be able to explain how ammonia is made in the Haber process by the reversible reaction of nitrogen and hydrogen. You should also be able to describe and explain the reaction conditions and be able to write a word and balanced chemical equation for the reaction taking place. And finally, you should be able to describe the uses of ammonia and a chemical test for the presence of ammonia gas. Now in this video we're going to look at the Haber process, which is one of the world's most important industrial processes, and it's named after the German chemist Fritz Haber, and it involves making ammonia, NH3, using nitrogen gas from the air. Now the reason it's one of the world's most important industrial processes is that without ammonia we wouldn't be able to make fertilizer, and without fertilizer 3 billion people would starve because we wouldn't be able to make enough food for the world's population. Now ammonia is an essential chemical needed not only for fertilizers but also is used in the production of nitric acid, nylon and explosives. And Haber was awarded a Nobel Prize in 1918 for his achievement of making ammonia from nitrogen gas in the air. Now plants need nitrogen to grow, and even though the air is made up of 78% nitrogen, plants are unable to use this nitrogen directly from the air. So in the Haber process, the nitrogen from the air is converted into ammonia, NH3, and the ammonia is used to make nitrogenous fertilizers, fertilizers containing nitrogen such as ammonium nitrate or ammonium sulfate, and plants are able to use the nitrogen in these fertilizers to grow. Now as you can see from this slide, around about 80% of the ammonia produced worldwide is used in the manufacture of fertilizer. Now other uses of ammonia include making nylon, and about 10% of the ammonia produced is used in the manufacture of nylon, whilst around 5% of the ammonia produced is used in the manufacture of nitric acid. Now ammonia is also used in the manufacture of explosives, dyes and pesticides. So now let's look in detail at the Haber process. Well, in the Haber process, nitrogen from the atmosphere reacts with hydrogen, which is usually made from the reaction of natural gas and steam, to form ammonia in an exothermic reaction. So we have a word equation here: nitrogen plus hydrogen forms ammonia, and the reaction is reversible, and this means that the reaction goes both forwards and backwards. Now you also need to be able to write a chemical equation for this reaction, and the chemical equation would be nitrogen, N2, reacting with hydrogen, H2, forming ammonia, NH3. And to balance this chemical equation, we put a 3 in front of the H2 and we put a 2 in front of the NH3. And if we do this, the chemical equation is balanced, as we would have 2 nitrogens on the left and 2 nitrogens on the right, and we'd have 6 hydrogens on both the left and the right hand side of this equation. Now the forward reaction, nitrogen plus hydrogen forming ammonia, is exothermic. It gives out heat. And the backwards reaction is endothermic. So ammonia breaking up into nitrogen and hydrogen takes in heat. Now for this chemical process, the raw materials are air, because that supplies the nitrogen that we need, natural gas and water. And the natural gas and water are used to make the hydrogen. Now natural gas is mainly made up of methane, and the methane would react with steam to form hydrogen. That's usually how the hydrogen is made. The nitrogen is taken from the air. Now the conditions for this reaction are: we need an ion catalyst. Now remember, a catalyst is a substance added to speed up the rate of a reaction. We need a temperature of between 350 to 450 degrees C, and a pressure of between 150 and 200 atmospheres. So now we're going to look at the reaction conditions a little more closely. Now, for any industrial process, there are two important factors: yield, how much product is produced, and rate, how fast the reaction is. And this reaction is no exception to that. Both yield and rate are really important here. And the reaction conditions are there to give us a reasonable yield at a reasonable rate. Now, the forward reaction is exothermic, and for exothermic reactions, a high yield is produced at low temperatures. Now, what we mean by this is that at low temperatures, the ammonia forms and is less likely to break up into nitrogen and hydrogen. In other words, the backward reaction is less likely to take place at low temperatures. Now, the problem with carrying out reactions at low temperature is that the reaction is too slow. And that's why a compromised temperature is used. And this compromised temperature, which is normally between 350 to 450 degrees C, gives a reasonable yield at a reasonable rate. Now, if we went at a high temperature, higher than 450, we would get a much faster rate of reaction. However, the ammonia would readily break up into nitrogen and hydrogen, and we would get a poor yield for this reaction. Now, in addition to having an iron catalyst and a temperature between 350 to 450 degrees C, we also have a high pressure of between 150 to 200 atmospheres. Now, this helps us get a good yield and also a good rate of reaction. Now, the graph on this slide should help you understand this a little better, because the graph shows the percentage of ammonia produced, in other words the yield, at different pressures and temperatures. Now, you should see from this graph that there are three plots here, and we're changing the temperature. And if you increase the temperature, the percentage of ammonia that forms decreases. You should also see from this graph that as you increase the pressure, the percentage of ammonia increases. So the yield of ammonia increases when you increase the pressure and decrease the temperature. So, for example, 450 degrees C may often be used in this reaction along with a pressure of 200 atmospheres, even though the yield is only 25%. And this is because a lower temperature, which offers a higher yield, will often be too slow. Now, you may be thinking that having such a poor yield, i.e. 25%, would be a real problem for this industrial process. However, it's not a major issue because the nitrogen and hydrogen that is unreacted simply gets recycled and put back into the reactor, and this makes the process very efficient. Now, chemists won't tend to use a higher pressure than 200 atmospheres, even though they would get a higher yield, and this is because it would be too expensive to produce equipment that would withstand such high pressures. Now, although the iron catalyst speeds up the reaction, over time the catalyst becomes poisoned and less effective at speeding up the reaction, and therefore would need replacing. So this diagram summarizes the overall process. We have nitrogen, which we get from the air, reacting with hydrogen, which we get from natural gas reacting with steam, and the natural gas is mainly in the form of methane, and this reacts in a reactor, and we have an iron catalyst. We have a temperature of 350 to 450 degrees C, and we have a pressure between 150 and 200 atmospheres. Now, the forward reaction between nitrogen and hydrogen to make ammonia is exothermic, and that means heat energy is given out, and chemists are able to make use of this because they're able to recycle this heat energy, which ultimately saves money and saves energy because you don't have to keep heating the nitrogen and hydrogen up to between 350 and 450 degrees C each time. Now when the ammonia forms, it's cooled and compressed, so it leaves the process as a liquid. Now any nitrogen and hydrogen that has not reacted is simply recycled and put back into the reactor, and that makes the process much more efficient, and that's how chemists are able to overcome the fact that they will have a low yield of ammonia, sometimes as low as 25%. So now we know how to make ammonia, let's look at the chemical itself. Now ammonia is a base, which means it's the chemical opposite of an acid, and it has a pungent smell, and when you dissolve it in water it forms the alkali ammonium hydroxide. Now to test for ammonia gas, all you need to do is place damp red litmus paper near to the gas, and if it is ammonia, this damp red litmus paper will turn blue. Now even though ammonia has a characteristic pungent smell, this is not a chemical test. The chemical test is to add damp red litmus paper, put it near to the gas, and if the gas is ammonia, the damp red litmus paper will turn blue. So now let's look a little more at the uses of ammonia. Now we've seen previously that ammonia is used in the manufacture of fertilizers and nitric acid. Now nitric acid has the chemical formula HNO3 and is made by a series of oxidation reactions from ammonia. And ammonia is also used to make fertilizers such as ammonium nitrate and ammonium sulfate, and we can represent these reactions with some word equations. So if we had ammonia solution reacting with sulfuric acid, it would form ammonium sulfate. Now likewise, if we had ammonia solution reacting with nitric acid, we'd form ammonium nitrate. Now ammonium sulfate and ammonium nitrate are examples of salts, and salts are chemicals made from acids, and any salt that is made from sulfuric acid is called a sulfate, and any salt that is made from nitric acid is called a nitrate. So we have ammonium sulfate here because the salt is made from sulfuric acid, and ammonium nitrate because the salt is formed from nitric acid. Now nitrogen-based fertilizers such as ammonium sulfate and ammonium nitrate are called nitrogenous fertilizers, and they provide nitrogen to plants which is needed for growth. Now using nitrogenous fertilizers can lead to increased crop yields and also healthier crops. And nitrogenous fertilizers are popular with farmers because they're relatively cheap as well. So now let's look at the disadvantages of nitrogenous fertilizers. Now the problem with nitrogenous fertilizers is that they dissolve in water and therefore they get washed into streams and rivers when it rains. And this causes a number of problems. And the first problem that we're going to talk about is eutrophication. Now the word eutrophication comes from the Greek language, and the U part, the EU part, means well, and the troph bit comes from the Greek word for nourished. So it means well nourished. And eutrophication is where too many nutrients get into streams and rivers. Now by nutrients we mean nitrates from nitrogenous fertilizers and phosphates as well, which are often used as parts of fertilizers, and these are great food for algae, and the algae feed on these and reproduce, and you get what we call an algal bloom. Now you can see the algal bloom here on the picture on the left because it's this green covering on the stream, and this algal bloom prevents light getting to the lower plants, and the result of this will be that the lower plants can't photosynthesize and they die, and the algae itself will use up all the nutrients and they will die as well. Now if the lower plants can't get any sunlight and they die, it means bacteria will feed on these lower plants, and these bacteria will remove oxygen from the water. And the result of this is that fish will die, and the whole food web is disrupted. So that's why eutrophication is a major environmental problem caused by the use of nitrogenous fertilizers. Now, the other disadvantage we want you to be aware of is the fact that these chemicals could enter the water supply and lead to conditions such as blue baby syndrome. Now, this is a rare condition where a baby's blood is starved of oxygen, and this lack of oxygen results in the skin of the baby turning blue, and the bluish tinge is more visible on parts with thin skin such as the lips and the earlobes. So that's the second disadvantage of these fertilizers, the fact that people are concerned about the risks that can happen if these chemicals enter the water supply, and that many people believe there are links between conditions such as blue baby syndrome and the increased use of nitrogenous fertilizers. So now let's test your understanding of this with some practice questions. So here's the first practice question. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So this first part of question 1 is asking you to complete and balance the equation below, which represents the formation of ammonia in the Haber process. So we have nitrogen reacting with hydrogen, and ammonia is the product, NH3. Now we need to balance this equation. So we have 3 hydrogens on the right hand side and we have 2 on the left hand side. So we need a number that 2 and 3 go into. That would be 6. So therefore we'll have 3H2, which will give me 6 hydrogens on the left. And we put a 2 in front of the NH3 to give me 6 hydrogens on the right. So there's 1 mark if you realize that it was ammonia as the product, and 1 mark if you got the correct balancing. Now it says state what is meant by the symbol shown here. Well, this means it's a reversible reaction. It's a reaction that goes both forwards and backwards. 1 mark if you said that. So here's the next part of question 1. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So part 2 is asking you to use the graph to answer parts 1, 2 and 3 here. So it says what happens to the yield of ammonia as the temperature increases? Well, when you increase the temperature, you can see from the graph that the yield decreases. So if you said the yield decreases, you get 1 mark. And then it says what happens to the yield of ammonia as the pressure increases? Well, as we increase the pressure at all the different temperatures shown here, it leads to an increase in yield. So the yield increases when we increase the pressure. 1 mark for that. And then it's asking you for part 3 to calculate the change in yield if the temperature is decreased from 500 to 450 degrees C at 350 atmospheres. So if we look at 350 atmospheres and we go upwards here, we look at the yield at 450, and that's 40%, and the yield at 500 degrees C is 30%. So we can see that the change is a 10% change in the yield. If you said that, there's 1 mark. So here's our second practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 2, you're given a graph which shows the percentage yield of ammonia at different temperatures and pressures, and you're asked to use the graph to find the conditions required to give a yield of 60% ammonia. So 60% ammonia is only achieved at a temperature of 300 degrees C. So I'm going to write this in now. So the temperature would be 300 degrees C. And if I look at the pressure required to give a yield of 60%, at 300 degrees C, it would correspond to 220 atmospheres. So there's 1 mark for the temperature and 1 mark for the pressure here. So for part 2, you have to sketch a curve for the percentage yield of ammonia at 350 degrees C. Well, increasing the temperature would decrease the yield. So you need to plot a graph, and it needs to follow the same trend as the other 2 plots. It just needs to be lower than 300 degrees C and higher than 500 degrees C. So 1 mark if you plotted a graph and it had the same trend as the other plots, and 1 mark if you plotted it correctly between the 500 and 300 degrees C plots. So part B is asking you to describe 1 advantage and 1 disadvantage of using nitrogenous fertilizers. Well, 1 advantage would be it increases crop yield, so you could say that. Or you could say that it gives healthier crops, you could also say that. And for a disadvantage, you could talk about eutrophication. That would be the obvious answer here, and the environmental impact of that. Or you could mention about the concern that people have with chemicals entering the water supply and the risk of conditions such as blue baby syndrome. So that would be okay as well. Now this is a 2-mark question, so there's 1 mark for an advantage and 1 mark for a disadvantage. So that concludes this video lesson. So after watching this video, you should now be able to explain how ammonia is made in the Haber process by the reversible reaction of nitrogen and hydrogen. You should also be able to describe and explain the reaction conditions and be able to write a word and balanced chemical equation for the reaction taking place. And finally, you should be able to describe the uses of ammonia and a chemical test for the presence of ammonia gas. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.